Okay, let's get started. So basically, in the last lecture, we finished talking about the analog communication, okay? So the material of the midterm will be ended until the last lecture, okay? So starting from this lecture, so that would not be covered in the midterm, right? That will be covered in the final. And during the spring break, probably I will upload 2 additional videos because we missed 2 classes before, okay? So I will try to upload 2 additional videos to make them up. Okay, let's briefly review what we covered in the last lecture. So basically, in the last lecture, we have 2 topics. The first one is the super heterodyne receiver, and the other one is applications of the angle modulation. In particular, we focus on the FM applications. Okay, so basically the idea of the super heterodyne receiver is that, so in practice, we can now design very high quality bandpass filter in any frequency, right? So basically, instead, what we do is that we design a very good high quality bandpass filter in some certain frequencies, for example, like these frequencies, right? And if the coming signal is not in those frequencies, then basically we're gonna shift the signal to those frequencies and then do the bandpass filter. Okay, that's basically the idea. And how do we shift the signal in the frequency domain? So this is the part that we're really familiar with, right? So basically we're doing multiplying by a cosine signal or by another carrier to shift the signal to the certain frequency that we want, right? So this is basically the idea. And from this figure, you can see that. I say this is our original signal, right? And then we design a local oscillator frequency noted as omega LO, right? If we multiply this kind of frequency, then we shift the signal to here, and then of course we're going to shift signal to the other side as well, right? But the downside here is that we have the problem of the image station, right? When we shift the signal to here by multiplying a cosine, so basically we're going to shift everything here we see, right? So if there's something here, so this signal and this signal is what we care about, right? So if we shift something, if we have something here originally, then we're going to shift that to here as well, right? So that can cause a problem, right? The way to solve this problem is to filter this guy out, right? Because we're just because the goal is not to keep something, but filter this kind of thing out, right? So the filter does not to be really precise, right? We can use a low quality filter to filter this guy out, right? And then to reduce the interference caused to this signal, okay? So that's basically the idea, right? So what we do is like this. So basically, we use the RF amplifier with a bandpass filter tunable, tunable to the frequency of omega C, right, to filter the image station out, right? Yeah, and then we multiply everything by a local oscillator field, by a signal with a carrier signal with frequency of the local oscillator frequency, and this is designed as the carrier frequency at the frequency of the intermediate frequency. Okay, and after that we have a high quality filter at the intermediate frequency, and then we filter the signal out, and then we do the detection and so on, right? So this is basically the idea of super heterodyne receiver. Okay, any questions? Okay, good. And then we talk about 2 applications. One is the FM broadcast radio, and I'm not going to go over this again. So we went over this in the last lecture. So basically, yeah, you can watch the video if you don't recall anything. The interesting part is this kind of figure, right? So for the audio, we need to transmit the mono part, and then we need to transmit the stereo part separately, right? And this part is FM, but this part is DSP-SC, okay? This is kind of interesting. And then we talk on the cellular communication, right? So which is the AMPS. So that's a very old cellular communication technology used in the US. Okay, and again, so you can see what we're doing there. So this is the analog communication system, right? Starting from 3G, I think this is 2G. I think starting from, or 1G, I forgot. But starting from like 2G, I think, then we're coming into the area, or 3G, coming into the area of digital communication, okay? So, which is what we're going to cover today, okay? Yeah, and I think this coming naturally to the idea of digital communication, okay? So, yeah, let's see some slides here. So basically, this is our today's topic, right? Today we're going to talk about sampling, right? Which is the key that from the analog to digital, right? So by the way, so when we talk about the digital communication, what do we mean? Right? We briefly mentioned that in lecture 1, probably. Right? Analog is that we transmit in the waveforms, right? So the signal is a waveform. Either the magnitude can represent the information, or the phase or the frequency can represent the information, right? But we're really transmitting the analog signals, right? For example, if for speech communication, right? So although we need to convert our signal from audio signal to electromagnetic signal, but still, that's more or less reflect our voice, right? So what is digital? Yes.
Like you're transmitting ones and zeros, basically.
Very good. It's 1 and 0s, right? But yeah, that is kind of further down into the hill. As a first step, so what do we do by converting from analog to digital is sampling, right? So basically, this is what we do. Yeah, I have a pen. So it is like, when we talk about signal systems, right? So basically, we talk about continuous time system and a discrete time system, if you still recall, right? So basically, so for a continuous time system, let's say here is a signal, okay? And we call that analog signal, right? But we can say this is like continuous time signal, okay? But for discrete time signal, we mean that we do some sampling here, right? If we take a point from here, 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 and so on, right? There is some, distance in between, like regular distance, right? Normally, we just take it, with equal distance, right? Let's say distance is TS, and so on, right? So this kind of signal is called discrete time signal instead of, yeah, of course, we need to do some normalization to normalize the length of the TS, right, to make all of these guys integers, right, from the definition. But here, for the digital communication, our goal is to transmit these signals instead of the entire waveform. That makes sense? Okay, so now the question is that, okay, so this is not our original signal, right? Our original signal is still this continuous time signal. Okay, but now we're transmitting something else, right? And we are transmitting this point, this point, this point, this point, and so on, right? So the question is that, are we losing anything?
You could. It depends how long your sampling time is.
Then exactly, very good. Yeah, but let's say our sampling time is not extremely small, but small enough. Do we lose anything? In other words, so by only receiving this point, can we recover the middle point exactly? Not roughly, exactly. Can we do that, or let's say, how should I phrase this? So intuitively, we cannot do it, right? Normally, but is there a condition that we can do it? For example, if the signal in the frequency domain is band limited, yeah, we're going to introduce the concept formally later, right? Band limited basically means that the signal, let's say in the frequency domain, is like this, right? We have a 0, have a B here, we have minus B here. So meaning that the signal does not changing too much, okay? Under these circumstances, is that possible that we can recover the middle point exactly? meaning we do not lose anything. Is that possible? Right? If you think no, I think that still makes sense. But if you think yes, when you think why, right? How come, by receiving only this small number of points, how can we get the middle point exactly without losing anything? The answer is yes, we can do that. But why, right? It's kind of magic, right? So, okay, so so this is the main part of, this, this and next lecture. So probably we're gonna see that by only receiving this discrete point, we can recover the entire signal exactly without losing anything, right? So this is the first intuition to tell us that we can use digital communication. We don't need to transmit the whole waveform. We just need to transmit all of those samples, okay? And that is enough to recover our audio or our video and so on, right? And transmitting those discrete points, the approach can be various, right? For example, we can use a digital sequence like 0, 1s to represent this value, right? By transmitting 0, 1s, and at the receiver side, if we see, this kind of sequence, then we can recover this guy exactly, and then we can recover the entire thing. Okay, so that's the first step, right? So, so there are some other advantages of, using this kind of communication, because now the entire idea is totally different. So before we're transmitting a continuous time waveform, there's no way, we just need to transmit it, either in a magnitude or amplitude or phase or frequency, right? We have to transmit this exactly. But now our goal is to transmit all these discrete numbers. Then there's a lot of advantages, right? So to answer the question, so we can see the list are just a few of the advantages, right? First, so we may need a lower power, right? And so it might be robust to the channel distortion, right? Because as we see before, so if we want to transmit that over the air, right, any noise will impact this guy directly. But if we transmit like 0, 1s, right, and the receiver side, we only need to recover 0, 1s. Let's say if we send a 1 analog signal, like 1, right, if you receive 0.9, for analog communication, you got like 10% different. But let's say if you got digital communication, if I say, okay, if it's above 0.5, it's 1, below 0.5 is 0, then if you receive a 0.9, it's still 1. You lose nothing, right? It's robust to the channel distortion. And we can also send more information, right? So this basically related to what we're going to cover next. So we're going to discuss that later. And the transmitter is kind of information agnostic, right? It doesn't matter, what kind of signal you transmit. It's all 0 and 1s eventually, because it's all, the number. So those will be all represented by 0 and 1s, right? So basically, yeah, either it's audio or video or whatever, all 0, 1s, right? Just see a lot of 0, 1s, right? It's kind of, information agnostic. And so this part is related to send more information. So in this way, it gives us a chance to understand the limits, the fundamental limits of digital communication. Yeah, I briefly mentioned that in our very first lecture, thanks to Klaus Shannon, right? So basically, if we consider digital communication, it is possible to characterize so how many bits we can transmit per second. Okay, actually per second per hertz, but it doesn't matter, per second within a certain unit bandwidth. Okay, we can characterize a number there. Okay, so this is amazing, and so this cannot happen in analog communication. So analog communication, we cannot quantify how much information we can transmit, but for digital communication, we can do that. Okay, actually we have a class on that in information theory that will be offered probably in spring next year. But so that course is to talk about this kind of fundamental limit for digital communication. Okay, and so if we understand this, then we can see exactly how much information we can transmit. Then we know, yeah, that means okay, we can send more information. Okay, also, as we said, we can have error correction and detection possibility, right? So this basically means as follows. So now let's say we transmit 0 ones, and the channel is an irregular channel. It means that, okay, so we just don't see some of the numbers at the receiver side, right? For example, if you just send a 1, and then if you didn't see anything in the receiver side, you lost a 1, which is not good, right? But instead, now let's say you transmit 3 times of 1, right? If you transmit 1 and 0 everything 3 times, right? If you got 1 lost, then you still see 2 ones, and you know it is a 1, right? This means you have the error correction capability, right? Okay, and the other thing is that we know how to storage information, right? Although storage and communication seems like different animals, right? But they are very, very similar, right? For example, so in storage, although there's no communication, but the storage cell can fail, right? If a storage file failed, then what do? We don't want that, right? So in our hard disk or SSD, we all have this protection mechanism. So that is done via the idea of digital communication. It's like error correction, right? If one cell fails, then we can correct it. Okay, yeah, that's why we mentioned storage of information is related to this. Okay, and and the other thing is digital communication is more friendly to use our DSP, right? Digital signal processor, right? That can be very powerful and power efficient and small, right? We cannot, or not that easy maybe to deal with complicated analog signals, right? Easy one might be fine, might be okay, but complicated, may not be easy to deal with. But we can use DSP to do lots of signal processing, okay? That's much easier to do in a digital domain. Okay, and the other thing is they call it no component variation. I think they mean the component variations is not much. Okay, yeah, those are just name a few advantages of using digital communication. Okay, so now let's see some concept. So an analog signal can be represented by its samples, which are values of the signal that are usually taken at regular intervals. So what do we mean is exactly this. Okay. So analog signal represented by these samples, right? And then we need to understand the implication of the rate at which signals are sampled and our ability to reconstruct those signals, right? This basically means that we need to determine at which rate of TS. So how clearly, the TS is smaller the better, right? Because if it's smaller, then we can get, more dense samples, right? But is there a limit? Right, so we cannot get TS as small as we want, right? So is there, a kind of not so small TS so that we can recover the original signal? Okay, so that's basically the answer of this question, right? We want to answer this kind of this question, and here are some definitions, right? General definitions. So they are kind of opposite to each other. The first one is called band-limited signal, right? So this basically means exactly this, right? The signal bandwidth is limited, right? So everything outside B is 0, okay? And on the other hand, so we also have the concept of time-limited signal. So you can imagine those are kind of dual signals, right? Because the relation between the time domain signal and the frequency domain signal, they are connected via Fourier transforms, right? So basically, they share the same similar property, right? This basically means that in the time domain, it's limited, right? That's it. Okay, so this is an important theorem. So basically, it's called the uncertainty principle. So basically, if a signal in the time domain, in the whatever domain, in the frequency domain is limited, so in the time domain, it cannot be limited, right? So in the time domain, it has to go forever, okay? And vice versa. If a signal in the time domain is limited, in the frequency domain, it will go forever. So which cannot make sense, right? Because in the time domain, if it's limited, meaning it got stopped, at some point, and here is a sudden change, right? And to describe this kind of sudden change, you need a limited, very high frequency component to describe this, right? That we can understand in this way, right? But this is very important, right? So signal if in the frequency is limited, time domain unlimited, right? Time domain limited, frequency domain unlimited, right? There's no such a signal that in both frequency and time limited. However, on the other hand, do we have a signal that have both unlimited in frequency and time? Do we have such a signal? Yeah.
Yeah.
Uh-huh.
Like a square wave.
Square wave.
A square wave.
No, square wave in time domain is limited, right? Square wave is this, right? So in time domain, so it's limited. Yeah, frequency is.
Like a periodic square wave.
Well, yeah, that's right. Yeah. But how about some regular signal, right? Because it's kind of artificial, right? If you have make it periodic, then we have to introduce delta signal and so on, right?
Yeah, I was thinking the pulse train, but it's kind of the same thing.
Yeah, but there are like much simpler signal, right? For example, if you try it, let's say E minus, this guy, yeah, I believe in both time and frequency they are limited. Yeah, let's try it, try Fourier transform of it. Yeah, there are many, right? So those are fine, right? So now let's be clear, okay? So in one domain limited, the other domain is unlimited, right? No signal in both domain limited, but there are a lot of signals in both domain unlimited. Okay, yeah, I think talk enough about that. Yeah, so those are give you some formal definition about sampling interval, sampling rate, and so on. Yeah, this is a signal we talk about. I think it's exactly this, right? And so here, the sampling interval basically means that the sample, the time between consecutive samples denoted by TS. S basically means sample or sampling, and usually measured in seconds per sample. And the sampling rate, is means how fast you sample the signal, right? It's nothing but 1 over TS. It's denoted by Fs, so it's 1 over TS, and so it's measured in samples per second. Okay, so those are the definitions of sampling interval and the sampling rate. Okay, great. And then okay, so next, our goal is to see, okay, how can we recover the sampled signal exactly, right? Yeah, how this magic can be done. Okay, so there's some mathematical trick that we're going to play here. So basically, it's called impulse sampling. Right, the idea is that, right? So basically, it is very easy to intuitively understand what the sampling is, right? Just take some point out from a signal, right? But mathematically, how can we describe this behavior, right? So the trick is to tell you how can we describe this behavior, okay? So it as follows. So now we let G of t so be band limited signal, right? And the bandwidth is capital B, right? So basically, it means this. So in the frequency domain, G of f look like this. Okay, so now next is how to describe the sampling process. Yeah, let me give you a hint, right? So basically, we kind of mentioned this before, right? Did you remember the sampling property of some signal that you remembered? Like delta signal, right? The delta signal is what we use, to sample signal mathematically, right? But here we're gonna use it in a slightly different way. Okay, not exactly the same way as before, but still use delta function. So basically, what we do is as follows: we define a kind of special delta function as a summation of a number of delta signals. Right? Does that make sense? So basically, this signal look like this, right? It's an impulse train, something like that. Okay. So this is our delta Ts of t, right? Just a bunch of delta signal, right? So what we do is that we use this signal and multiply gt as a sampling behavior. Okay, so let's see what are we doing here. So basically what we do is as follows. So let's say the g look like this. Okay, and yeah, delta, the distance, yeah, maybe let me write here 0, here's Ts, 2Ts, 3Ts, and so on. Here's minus Ts. Here's minus 2Ts, and so on. Yeah, this is GT, right? So basically, what we do is as follows. We use this guy, multiply this guy, okay? And then see what we get, right? So maybe I'll use another color. I'll make it down a little bit. Let's see, here's our g of t. So basically, what we do here is that we have a signal here, right? And we'll have signal here. And here's 0 point. We'll have somebody here. And here there's another one. Ts, 2Ts, 3Ts, and so on, right? We use this, multiply that, and equal to this. Okay, so what does each of this arrow mean, right? So this basically means that it's a weighted delta signal, right? So this basically means that we have G naught multiplied delta T, right? And how about this guy, right? So that's the G Ts multiplied delta T minus Ts, right? So how about this guy, right? That guy basically is G minus Ts delta T plus Ts, and so on, right? So each of the term is a weighted delta signal. That makes sense, right? And we call this guy as a sampled signal, right? Does that make sense? Right. So basically, the value here basically represented by the weight, but each of them, we need to multiply each of them by a delta signal, right? There's some mathematical advantage of doing this, as we're going to see later. But this is what we mean by impulse sampling, right? And this is a mathematical trick that we're playing. We define the sample in this way, okay? So by the way, let me ask you a question. Okay, after this, multiply that, we got this signal. So is this signal continuous time or discrete time? Discrete time? How about others? Do you all agree? Everyone?
I'm not sure. We're still using t, not n, so that's why I'm inclined to say it's continuous.
Very good. Still, it's not discrete time, it's continuous time. There are a few reasons. One reason is that, G of t is continuous time signal. This is a continuous time signal, right? We have two continuous signal multiplied together. there's no way to get a discrete time signal, right? So the other thing is that, okay, so discrete time signal only defines on the integer point. All middle point have no definition, right? Yeah, so here, although we have TS, even if TS is 1, then it's still not a discrete time signal because so all those values are 0. It's defined, right? But discrete time signal only defined in the integers. Does that make sense? Right? You know, it's kind of fake, right? It's a mathematical definition, but it's defined in that way. Okay. And the other thing is that we still have the direct delta signal. In discrete time signal, we don't use direct delta. We use Kronecker delta, right? So this is still continuous. Okay. Converting from continuous to discrete is trivial. You know, we just normalize everything by 1 by TS, and then make the middle part undefined, and change it to Kronecker delta. Then that's it, right? It's not, but just, you know, precisely speaking, it's still continuous time. Okay, great. So let's write it down. So we denote, so this signal, the multiplied signal, as g hat of t, g bar of t. Okay, and then we can write g bar of t. So that equals to gt multiply, delta tst, right? That is gt multiply a summation of a bunch of this delta. So now our idea is to analyze this guy, right, and see, you know, what are the property of this guy in the time domain, and what are the property of this guy in the frequency domain, so that let's see whether we can recover the original g of t exactly, right? This is our goal. Okay, so now let's try to analyze this guy in the time domain, see how it looks like, right? And then clearly, so we can put this guy in, right? So it's a gt multiply delta t minus nts, right? And that is so here, because delta t is only non-zero at n times ts, right? Then we can replace this t by n times ts, delta t minus nts, right? So we arrive here. Okay, so what should we do next? So can we still do anything? Yeah.
You can take the Fourier transform.
Oh, very good, right? So yeah, we're gonna do that later. But from the time domain, so my point is that it's very hard to see anything, right? Then we should think about this guy in the frequency domain, right? Very nice. But before doing that, so let's have another try, right? So basically, we almost have not used this kind of trick before, a little bit, but so clearly this guy, or this, so that is a periodic signal, okay? If you remember, it's a very, very weird signal. So we have seen this signal before. We did the analysis of this signal in very detail. So we compute the Fourier series of it. We compute the Fourier transform of it, right? If you remember, the Fourier transform of this guy is another sum of delta signals, right? So basically, if we want to analyze anything in the time domain, so instead of directly use this signal, so we can maybe look at this Fourier series expansion. Okay, normally we don't do that, because normally that will not give us a lot of benefit, right? But for this guy, so its Fourier series may look very interesting, right? If you still remember, so let's try to do that. Okay, so let's try to compute the Fourier series of this guy. Fourier series. Okay, and who do you remember it? Kind of very easy form. doesn't matter. Let's compute it because it's really straightforward. So basically, we denote the Fourier series of this guy's dn, right? From now on, we just compute the complex exponential Fourier series, right? Just write down definition here. So basically, here we have 1 over Ts, and then we do the integral within one period, right? And then we write this guy, e minus j 2 pi k. And yeah, should we use n, right? So here's n. Yeah, maybe I use omega. And omega s t dt, where omega s is the sampling rate, in radian. So that is what, 2 pi over ts. Okay, so that's the definition of the Fourier transform. But remember, the trick here is that we do the integral over one period, right? So the period that we pick is this period, right? We do the integral from here, minus ts over 2, to here, ts over 2, right? So this is the period that we're doing for the integral. And within this period, so delta ts will become just a delta signal, right? So this is basically what we did before. So that is 1 over ts, and this one becomes a delta signal, e minus j n omega s of t dt, right? So when you see this, you should be pretty happy, right? So then what you should do? Have a delta here, and we have a function here. So you just need to put this guy, t, equal to 0, right? And then do the integral. So basically, what we have is what? If I put a t equal to 0 here, so this guy will give you a 1, right? And you just integrate a delta signal, that will be 1, right? So this guy will just give you a 1. And then 1 over ts is what you left. Okay, so remember, this is for all n from 0 to minus plus 1, minus plus 2, and so on. Okay, so it's kind of interesting for this kind of periodic signal. Its Fourier series has only it's a constant for all the n. Okay, and given this, so let me write here. Given this, okay, we can write down its Fourier series expansion or the synthesis equation. So that is nothing but 1 over ts, and then we do a summation. We can write that in this way, right? So this and this, they are equal, right? Okay, so now we can write the time domain signal like this. So that is the delta signal multiply the g of t, right? So that's basically equals to 1 over ts g of t minus ej omega s of t, right? We can write signal in this way. Okay, so from here, it's pretty clear that what we are doing, right? So what is this? gt multiply a phase term. What is that? Or what does it mean in the frequency domain? Exactly, right? In the time, it's a phase shift. So in the frequency, that will be a frequency shift, right? Because of this, we can directly write down its Fourier transform. Okay, so its Fourier transform equals to what? Basically equal to this 1 over ts. And so, yeah, we assume its Fourier transform as a gf, right? So that's nothing but, let's say, n. And we have a gf minus n omega, no. Yeah, let's use f, right? N minus fs, right? We can manipulate this a little bit because 1 over ts equals to fs, right? The form is kind of neat. So we can write that in this way. or we can change everything to 1 over TS. Right, this is how we do it. Okay, so from this way, so it's very easy. We can get a frequency domain representation of the signal. Okay, very good. So now let's draw it and see what happened exactly. So now let's assume GF looks a little bit nicer. So like this. And here's B, here's minus B, and 0. A triangle. Okay? So now, after the sampling operation, so what does GF bar look like? Right, so basically now let's see what is this operation here. Right, we have scaling factor here, but this is nothing but what? So we kind of seen this before. Or we look at this, it's easier. Right, GF minus NFS. So it's very similar to this guy. Right, meaning that we have 1 before. Now we add a lot more to make it periodic. Right, same thing happened here. Right, we have a GF here, and then so when n is 0, so when n is 0, we have 1 part here, so that's 1 over TS GF. Okay, when n is 1, we shift this guy to the left. Okay, so here's B, here's minus B, here's 0. Okay, and this guy is 1 over TS GF minus FS, right? And then we'll have another one here, right? So this is 0, this is FS, this is 2FS. That's 1 over TS GF minus 2FS, right? And on the other hand, on the left, we also have one part here, and this is minus FS, and this is 1 over FS, 1 over TS GF plus FS. And so on. Right, so this is how GF bar look like. So from here, we can see at least one thing. So GF bar has to be periodic, right? So this is kind of very interesting. Now, let's remember, let's refresh it, right? So basically, so in the time domain, the signal looks like this, okay? It's a sample signal. Right? Before a signal look like this, after a sample look like this. Okay? So the signal in the time domain, so the original signal in the frequency domain is like this. So that is continuous time and aperiodic, right? And after the sampling, it becomes still continuous time, but periodic, right? So this basically means that the sampling in the time domain result in the periodicity in the frequency domain. That cool? Or that is familiar a little bit? Yeah, let's think about the Fourier series. The Fourier series is what? It's the opposite. In the time domain, it's periodic. But in the frequency, it's discrete. It's like the sample signal, right? It's the opposite. Okay, great. Okay. So now I think it's pretty much clear on how we recover the original signal GF exactly, right? How can we recover it? Right, this is our sample signal. Okay, how can we recover this guy from here? Yeah.
But you can't pass it.
Exactly. Yeah, we can do something even easier, right? We just do the low-pass filter, LPF. And then everything will be gone, and we'll have that exactly. Does that make sense? Yeah, that's how we do that. So this basically means that we can recover the original signal exactly from the sample signal, right? All the missing information will be recovered exactly. This is what the math tells us, right? Now let's see the condition, okay? The condition of it is that, so all of this guy has to be separated, right? If they're not separated, there's some overlapping, then we cannot recover this exactly, right? So what are the conditions here, okay? Let's see, this point is B. What about this point? This point. Fs minus B. And we need to make sure this point and this point do not overlap. Or this point has to be smaller than this, right? So we require, maybe I'll write here, B less than Fs minus B. So that basically means that Fs bigger than 2B, right? So this is called the Nyquist sampling rate. Yeah, we mentioned this once before when we talk about the FM modulation, right? We sample the signal, right, with the Nyquist sampling rate, right? But this is Nyquist sampling rate. So we need to sample at least as fast as 2 times the bandwidth of the signal. Does that make sense? Okay, yeah, this is what we want to cover here. Okay, so in the frequency domain, it's very clear what is happening. So we just use the signal multiplied by low band LPF, and then we can recover that exactly, right? The only thing we require here is that the low, of course, this is wide enough, right? But the low-pass filter will have a scaling factor of Ts here, okay? Because we have 1 over Ts here, then we need to recover this constant. We just use Ts multiply the low-pass filter. Next, we want to see what happened exactly in the time domain, right? In the frequency domain, it's very clear, right? But what is happening in the time domain? So in the time domain, this is what happened. So remember, in the frequency domain, it's a multiplication. In the time domain, it should be a convolution, right? So yeah, because this low-pass filter is like this, right? And let's see. So now, let's assume the low-pass. We sample that. How to say? So we assume the width of a low-pass filter is exactly at B here. Okay. So for simplicity, so this is B. This is minus B. So basically, the low-pass filter looks like this. H of F in the frequency domain is Ts multiply the rectangle signal, right? F over 2B, right? F over B meaning here is B half, right? So this F over 2B. So now let's see what happened in the time domain, right? So in the frequency domain, we know that our GF equals to GF bar multiply HF, right? So in the time domain, it's a convolution. GT equals to this guy. So let me see. Now let's try to write it as this. So what we derived before. Okay, and then we need to convolute the time domain signal of that, right? The time domain signal of that is nothing but a sync signal. So that is nothing but a 2B times Ts. Yeah, you can work it out. So it's just a Fourier transform of this guy, right? So that is a sync 2 pi bt. Okay, and then, oh, I remove it. I don't want to. So basically, we convolute this delta with that should be easy, right? We just need to replace this guy by this guy, right? And here we do some simple assumption. We assume that the sampling rate, Ts, that's exactly equal to 1 over 2b. So basically means that we're sampling it at a Nyquist sampling rate. So this guy will be gone. That's 1 to make our life easier, right? So that's 2 pi b t minus nts, right? So this is what we got. Okay, Let me try to finish. So we're a little bit out of time. Yeah, but I just need 1 more minute. So this formula actually is very cool. Okay, so what does this formula tells you? Yeah, let's think a little bit. So when I draw this, right, so these are GT bar. Okay, so what the cool part of it is to tell you this, right? We know that in the frequency domain, so it's kind of easy. We just use a low-pass filter to get this out, right? But in the time domain, so we only have this kind of discrete point. How can we recover the middle part exactly? Right? We need to do some form of interpolation. Exactly. We need to do some form of interpolation, right? One idea is just to connect these 2 points. Right? That's a good way, right? But that is not going to recover this exactly. So the right thing to do here is so-called the sync interpolation, right? So basically, it means that we replace each guy of this by a sync signal, like this, right? And then second is again this, and so on, right? So each of them will be replaced by a sync signal and add everything together, right? Because remember, sync function has to go forever. Add them together, then we're going to recover this exactly, right? So that's one of the beauty of the Fourier transform, right? Fourier tell us if we do this, we can recover this exactly. Okay, yeah, I think that's it for today. So next lecture, we're going to talk about aliasing in detail, okay? And practically, how can we do the interpolation? You may think, this is very beautiful, right? But is that practical? Can I do that in practice? The answer is no, right? But we're going to see how we can do this in practice. Okay, great. Thank you. And I'm going to upload an old exam very quick, and then you can see what we did last time.